Have a look around you. Just about every piece of tech you use, every gadget you love, is powered by something we totally take for granted, the electric circuit. Today, we're going to peel back the curtain and really dig into the intricate physics that makes it all possible.
All right, just a quick heads up before we dive in. This is our advanced explainer. So we're going to assume you're already familiar with the basics of electricity, things like voltage, current, and resistance. If you're feeling a little rusty or want a refresher, you should definitely check out our first explainer on this topic. So, here's our game plan. We'll kick things off by moving past those simple analogies and getting into the real physics. Then, we'll explore the fundamental laws that are the rulebook for everything. From there, it's on to different circuit layouts, the big split between analog and digital, and some really cool real-world systems. And we'll wrap it all up with the 5 big ideas to take away.
Okay, first things first. It's time to graduate from the simple comparisons and get into the real meat of circuit theory, the core principles that actually make these things tick. So what exactly is an electric circuit? Well, at its heart, it's a closed loop, a complete unbroken path. Think of it like a racetrack for electrons. You need a power source, like a battery, to give them that initial push. You need a load, which is just something that does useful work, like a light bulb. And you need the conductive path, the wires, to connect it all. If that path is broken anywhere, you've got an open circuit and everything just stops.
Now, you've probably heard the whole electricity is like water analogy. And you know what? It's a pretty good place to start. But to really grasp the complexity we're talking about today, we have to leave the plumbing behind and step into the world of physics. And that means we need to speak the language of math, specifically Ohm's law and Kirchhoff's laws. In the universe of direct current, or DC circuits, there are a few star players. You've got your power source, the EMF, providing the voltage. You've got resistors, which are kind of like speed bumps for current. Then you have capacitors and inductors. These are the energy storage specialists, each with its own cool trick. And of course, you've got switches, which give us the simple but powerful ability to turn things on and off. So, we know the components. Now let's get into the rules of the game. These are the fundamental, non-negotiable laws of physics that are the bedrock for analyzing any circuit you can imagine. First up, the big one, Ohm's law. This beautifully simple equation, V equals I times R, is the absolute cornerstone of circuit analysis. It elegantly describes the relationship between voltage, current, and resistance. Honestly, it's the first tool you'll grab from your mental toolkit every single time. Let's see it in action. Let's say we have a simple 9-volt battery hooked up to a 10-ohm resistor. We can use Ohm's law to figure out exactly how much current is going to flow. We just shuffle the formula around a bit. Current equals voltage divided by resistance. Plug in the numbers, 9 volts divided by 10 ohms, and we get 0.9 amps. It's clean, it's predictable, and it's incredibly powerful. But what happens when circuits get more complex, with multiple loops and intersections? That's where Kirchhoff's laws come in and save the day. His voltage law is all about conservation of energy. It says that for any closed loop in a circuit, all the voltage gains and drops have to cancel each other out. They have to sum to 0. Then his current law is about conservation of charge. It says that at any junction, whatever current flows in must also flow out. Nothing gets lost. These two laws together let us solve just about any circuit you can throw at us. Now, these laws work everywhere, but how they work depends a lot on the circuit's architecture. How you arrange your components isn't just a style choice. It fundamentally changes the behavior of the entire system. The two main layouts are series and parallel. A series circuit is like a one-way street. The current has only one path it can take, so the current is the same everywhere, but the voltage gets shared or divided among all the components on that path. A parallel circuit, on the other hand, is like a highway with multiple lanes. The current can split up and take different routes. Here, the voltage across each lane is the same, but the total current gets divided among them. And this difference shows up in the math, which is super interesting. To find the total resistance in a series circuit, you just add them up. Simple. R1 plus R2 plus R3, and so on. But for parallel circuits, it's a bit different. The reciprocal of the total resistance is the sum of the reciprocals of the individual ones. It's a key distinction. Let's make this real. Imagine 3 10-ohm resistors lined up in series connected to our 9-volt battery. The total resistance is easy. 10 plus 10 plus 10 is 30 ohms. And that 9 volts from the battery, it gets split evenly across the 3 resistors, so each one gets a 3-volt drop. Makes sense, right? But now, watch this.
Let's take those exact same 3 resistors and hook them up in parallel instead. The whole game changes. The total resistance plummets to just 3.33 ohms. Why? Because you've created more paths for the current to flow, making it easier overall. Each resistor now gets the full 9 volts, and the total current being drawn from the battery skyrockets to 2.7 amps. Totally different behavior.
Okay, so we've covered the structure of circuits. But what about the information they're designed to carry? This brings us to a huge concept in electronics, the great divide between analog and digital. So what is the difference, really? Think of it this way. An analog signal is like a smooth ramp. Its value can be anything along a continuous spectrum. A digital signal, however, is like a staircase. It can only be one of a few specific values, usually just on or off, a 1 or a 0. There is no in-between. And this quote right here, this gets to the absolute magic of digital. Because every single logic gate cleans up the signal, snapping it back to a perfect 1 or a perfect 0. Engineers don't have to worry about all the noise and distortion that plagues analog design. This is the reason we can build chips with billions of transistors that actually work reliably. And this fundamental difference changes the building blocks you use. Analog circuits use components to carefully mold and amplify those smooth, continuous signals. But in digital circuits, we're basically using transistors as incredibly fast switches. We connect them together to make logic gates, and those gates become the foundation for all computer logic and memory. All right, enough theory. How does all this stuff actually come together in the real world? Let's check out how these components and ideas create the complex systems we use every single day. These components are really the unsung heroes. Capacitors are masters of storing up energy and then releasing it in a quick, powerful burst. Think of a camera flash or even a defibrillator. Inductors use magnetic fields to resist changes in current, which is crucial for things like tuning radios or in proximity sensors. And resistors provide that fine-tuned control, precisely limiting current and dividing voltage wherever it's needed. But the truth is, most modern devices aren't just one or the other. They're what we call mixed signal circuits. They have to live in both worlds. They use analog parts to sense the real world, which is messy and continuous. And then they use analog to digital converters to turn that information into clean digital ones and zeros for a processor to work with. Your phone is the perfect example of this hybrid frontier. Okay, let's bring it all home with 5 core principles to remember. Number 1, a circuit has to be a closed loop. No gaps. 2, Ohm's and Kirchhoff's laws are your mathematical foundation. 3, series versus parallel. The layout is everything and dictates how the circuit behaves. 4, the analog versus digital divide defines how information gets processed. And finally, number 5, advanced components like capacitors and inductors give us incredible power to store energy and shape signals. And this all leads to a final, mind-bending question for the future. We've pretty much mastered the classical physics that govern these circuits. But as we keep shrinking them down to the scale of individual atoms, we're stepping into a whole new world. What new physical laws, what quantum effects will start to take over and redefine complexity as we know it? It's something to think about. Thanks so much for joining me.